Hi, all right. Thanks for having me, first time speaker. So I want to talk about getting rid of It Works in My Machine. So a bit about me. I'm an embedded software engineer at Blue Current in the Netherlands. We make AC chargers for electric vehicles for home use. And apart from writing embedded software, I sometimes also work on some tooling and CI to make our lives more easy. So yeah, the big problem, there's so many chip vendors for every single component that you have on your board. And it goes from like deeply embedded small AVR chips all the way to like Linux systems with some custom Renaissance chip or whatnot. And every vendor also has some tooling that gives you either a code generator for some clocks for peripherals or a build root for your Linux distribution. And when you work on a team with multiple developers, inevitably someone is going to click on the update button and it will have a mismatching version compared to the rest. Maybe it's all fine. Maybe there's a subtle bug or a default changes, and then you have big issues that are really hard to track down. So how it goes wrong again, accidental updates, version mismatches. Sometimes it's also just a system update. Has nothing to do with the tools. It's just that Ubuntu decides to update or Windows updates breaks something. It's difficult to deploy changes. So if you have a big project and you want to update the library or whatever, you need to mostly do it manually. You tell your colleague, oh, go install that one tool version 5.7.1 and not the .2 because that one has an issue. Hopefully your colleagues all manage to do it correctly, but it's pretty hard. And when you have multiple projects, you might have multiple STM chips that have like different firmware versions of like the firmware support package, and that inevitably also becomes very hard to manage. So how can you fix this? There's three main ways that I found. The last one, I wasn't really aware when I fixed the issue at our company. So there's virtual machines, Docker, which is kind of a virtual machine, and then there's NixOS or DurEnd, depending on which part you want to use. So the virtual machines are quite cool. They're very stable. It's just running an entire computer basically on your computer. So you have your own file system, everything's isolated, it works on basically all platforms, and you can pass through your devices, have dedicated performance. But they're a big resource hog. So if you want to quickly switch between projects, it's really hard. You need to spin up the entire virtual machine and then save states, etc., etc. You keep the same maintainability and deployability problems where it's still a full OS, it still can get upgrades, and they're still modified by the user. So they might click on update. Then there's Docker, which is not quite a virtual machine. It's more like a full file system that replicates a distribution, and it just changes root to that, and then it can't really escape anymore. But you can think of it as a virtual machine. But the configuration is basically code that you can check in with your project. And that makes it so that it's versioned with the project. So you can switch back to like an older version, just git check out whatever the old version was, and you still have the entire environment as it was back then. And it's really fast to switch between projects. You just start the image. But it has quite a learning curve, especially for the implementer, but the users don't have to learn as much. So you can just dedicate it to one person. This time it was me. And it's not fully supported on all platforms. Like the newest macOS M1 chips don't yet support USB pass-through, so you can't do everything in the container. But more about that later. And then there's NixOS, which is a Linux distribution that's built from the ground up to manage versions and be reproducible, basically. And what it does is per folder, you can tell it what the requirements are for that folder, and it will just make sure that everything is in the path at the exact version you've been. And so you change directory, and then you have the tools available. The biggest con here, again, mostly learning curve, and this time everyone has to learn it. And not many tools are aware of NixOS. So you might have the correct version on your path, but unless you start the tool from that specific shell, it won't have the path set correctly. So a bit difficult. We ended up going with Docker. We tried virtual machines for a bit, but wasn't that popular. So how it works, the basic idea is that you describe how the image is built, and you make changes to a file system. So you run commands, and every command is embedded as a layer, and it just keeps kind of like a diff between layers, and that's a hash, and then it can detect if there's a change or not. And when you make a change to the description, only the parts below your change are rebuilt because the upper parts aren't modified. So a small example here, you'd have the base layer is from Ubuntu, so you import another image basically, which has all its own layers, and then you can modify it. So the first thing you do is you copy your application folder to there. That creates a new layer with the difference being only the files of your application. And then you run make, and then the result of that operation is stored as a diff of files again. And then you can run the app, and that's the last step. So that's what would happen if you run the image again. And then it makes a virtual layer, which is like the actual container when you run it. And there you can just do whatever you want. Eventually, you can even save it back as a layer to reuse the next time and make that reproducible. And it's quite efficient because every layer is stored as its own subset. So as you see on the right side of the image, there's a bigger part, which is like 180 megabytes. But then if you make a small copy of your files, it might only be a few hundred kilobytes, and it only saves that part. So you don't have to have the full layer again for every single instruction you give it. So then I have a sample Dockerfile. It's quite a bit of code, but don't be alarmed. It's pretty easy. So in our case, this is for ESP32 development. And so they provide already a Docker image, which has the IDF, which is their framework for developing things at a specific version. So we're using 4.4.1. And by using that image, those tools are already set up. Then we decide, oh, you know what, we need some more tools. We want to have libUSB. We want to have curl and git and make and cmake and some other cool stuff like fdfind for faster searches on your file system. And then we just set up the environment so we can export all the variables so that if you just run IDF commands for that specific toolchain, it knows where to find them. You can add a user so that you can SSH into the container as that user and do your things over there. And then there's some details like making an entry point, because when you run a container, usually it's a command. And so this entry point just sleeps indefinitely, basically, so that the container keeps running and you can just go into it as if it was a machine somewhere else. And this is pretty extensible. So, for example, if you want to add STM32 support to the image, one way of doing it, I'm not saying this way, is to just add the installer. So in here, what I do is I copy the installer, specific version that you can save somewhere. It's a shell script, but it's just a very, very big archive, actually, self-extracting archive. I modify the install folder a bit, such as saying, oh, you know what, I don't need the Segger tools, I'm sorry. We already accepted the license because I've read that before, and I've already made sure that I agree with this. And then I just run the setup. So it installs somewhere in the /opt directory. And now I have STMcube IDE in the container. And I can run it and get the graphical user interface as well on the main PC. And use the code generation tools, etc., etc. And that's all just pinned to the specific version that I embedded in the container. As well as that, I modify the environment variable so that the path is set. And if I run arm none EABI GCC, it picks the one from ST and not another one. Maybe you want to use some Clang tool, such as for the LVM project from the previous talks. One way to do that is just to add the packages to the installation. So here we get a newer version. This is version 15, which isn't on the Ubuntu repositories. So just on a bit of code, add their key, install the packages, clean it up, and then all you can have left is Clang tidy, Clang format, and the actual compiler. And you can do this for a lot of tools, and now every developer has the exact same one, which is great. But then you have to make a choice somewhere. It doesn't really matter how you do it. We've landed on making a Dockerfile per project. So we have one big project, which is the charge point, and it has multiple microcontrollers. And so we have right now an image which contains every tool you need to build the entire project. So we have ESP tools and SCM tools and whatever else you want. But you could also say, oh, you know what, I need that one image or that one container just for SCM chips or just for the ESP chips. So you could do it per platform, or you could even do it per team, where you say, oh, you know what, the embedded guys really want to use these tools always and have them available. And the persons that work on like the server-side stuff they want those tools, and that way the whole team always has the same tools for every project. It's more like what your own preference is. So the result of all this is you have a Linux-ish system, where you have all your tools installed, which you can just use from the command line, but you could also use it from an editor. It's like the talk that Jonas gave yesterday about making VS Code a cool environment for Zephyr. You can do the same thing with VS Code. You could do it with CLion. You could do it with anything else, your Vim or Emacs versions, because it's just a shell. It's just an environment in which you run things. And then some tools such as VS Code have abilities that are special, that just inject their backend in the image so that it's more performant, and then run the front end on your local machine. And other tools such as CLion don't, so you could just install CLion in the container as well and run from there. So there's still a lot of variation and personalization in how you want to set it up, but it works pretty well. That was it. Hope I'm still within time. So if there's any questions, I'll take them.
Yeah, thank you very much. That's a question.
Hi, thank you for that presentation. I actually have two questions. One, it's about have you tried to enable debugging from the container in the PCs of the developers? Like if they have like a probe, how have you handled that?
Yeah.
And then the second question would be about one specific line on the Dockerfile that you had, where you have the user add. Maybe if you could comment a little bit on that line. I'm quite interested in what you're trying to achieve with those. Thank you.
So first about the debug probe. Docker on all systems except for the newest macOS chips supports USB pass-through. So you can just attach your ST-Link or your J-Link debugger, and it will appear as a USB device in the container. And so you can just run all your normal tools from there as well. And it will just have access to the debugger. So for VS Code, you can just step through things, or you can use your STM cube and just also step through and flash and everything from the container itself. And you were asking about a specific line. This one?
Yeah, the group add line.
Group add that has to do with file systems and how they're mounted. This is more of an implementation detail for how VS Code goes into the container. By default, when you make a container, you're just root. And when you have a Windows path mounted through WSL to a container, and you edit something from the container, it messes with the permissions and makes them unreadable and writable from Windows. So by doing this, VS Code enters as itself, as a user which has the same user ID as the actual user on the PC, and then there's no more permission issues. So it's an implementation detail for VS Code, but if you don't use that, then you don't need it.
Okay, thank you very much.
Thank you very much. Any more questions? Oh, yeah.
On your slide where you had different options to organize for different project levels,
Yeah.
is there a way to compose Docker files? Let's say you have a Docker file fragment for one microcontroller, for another one, and for another one.
Yeah,
Then
so that's...
Then you want to mix and match from that in a, let's say, call another Docker file from a main Docker file.
Yeah, so that's actually exactly what the from command does here, is it imports another image, and it used to be that it was mostly normal to only have one big from, and then you extend one image. But nowadays, it's more and more common to also import specific layers from other images. So you could have one image for your ESP chip, one for the STM chip, and just import the results of that into your project image. And so you could have multiple froms that say, oh, you know what, from my ESP image, I want to get the environment, and then from the STM image, I want to get that, and then just combine that in one project Docker file.
Thank you very much. Any further questions? So many questions.
Thank you. One question: do you really force your team members to use VS Code?
No.
Thank you.
So that was one of the things, is we also wanted to keep the editor freedom. So a big part is moved on to VS Code, but I personally prefer CLion. We have one developer who prefers Emacs. So
I'm curious how the GUI part works. So do the GUI clients actually run outside of the Docker and
Yeah.
plug into the Docker, or can you actually run a graphical client inside of the Docker?
So you run the graphical client inside of the Docker, and then what you do is, since the Docker doesn't have an X server, you forward it to your distribution, and that works both on Linux systems and WSL, Windows Subsystem for Linux on Windows PCs, because they have gotten X server recently with the Windows 11 upgrade, and so you can launch a thing and we'll forward it to WSL, and then that just shows the X server that's built in.
But that only works with X, not with Wayland.
No, actually, Wayland also works, and it is more performant on the WSL as well.
Thank you very much. Further questions? No?
For CLine, you have two options. Either you install the client in the image, and then you use JetBrains Gateway, which is in beta right now, to connect to SSH to it. And then the backend runs in the container, and then your front end on your PC, but that's more limited. Or you can just install the full CLine in the container and run it as a graphical user interface app.
Any further questions? No? Then, this was Florian Humblot. Thank you very much for your time and a great talk.